Alright, this video is on the electrical field. So in a previous video we talked about the fact that an electrical field really only cares about charges. So it doesn't matter whether you're heavy or light. All that matters is what is your charge. And so the formula is very simple. It's got a couple of things that are tricky though. So here's our formula here. And I'll write down what all these things are. So the first thing, E in the little absolute value pipes with the little arrow up top, that's the field strength, and that is measured in newtons per coulomb. Newtons, remember, is a measurement of a force. Coulomb is a measurement of charges. So that means that the field strength depends on the charge. That makes sense. Now, we've got a letter K here. This is the electrical constant. And your brain's going to cry when you see the units for it, but I'll promise you that we'll make it as painless as possible. And the electrical constant is 8.99. So far, so good. Times 10 to the 9. Okay, so it's a big number, but that's not the worst thing yet. And it is given this unit here, Newton meters squared per coulomb squared. That sounds scary, but just watch. Everything is going to be beautiful, and it'll all come out in the wash. I promise you. Q is just our charge. Remember, that is measured in coulombs. And R squared, this is the distance from center of field. And it's going to be measured in meters times meters, which are going to be meters squared. Important to note here that meters squared on the bottom, what it means is that if I say I was at a distance of 1, my denominator here would be 1 squared. So 1 times 1 is 1. So whatever value I'd have on top, I would divide by 1. If I have a 2 down here, though, 2 squared is 4. Which means that if I double the distance between myself and the field, the power, the strength of the field, how hard it pulls, is 1/4 as much as it was when I was at a distance of 1. What happens if I am at a distance of 3? 3 squared is 9. That means that the power of the field is 1/9 as strong as it was when my distance was 1. So that means that this denominator, this number on the bottom, gets very big very quickly. That's why fields get super, super weak when you go farther away from them, because of this r squared on the denominator. We're going to see the gravitational field, it rhymes. It has the same denominator of r squared. But for now, let's just talk electrical field strength. So here we go. So what is the field strength of an electrical field that has a charge of 1.25 times 10 to the minus 5 coulombs at a distance of 3.00 meters? Okay, so all we need to do is take a look at our formula, take a look at all the things that we have been given. So K is always the same. So that doesn't change. My radius is 3.00 meters, which means I'm just going to cheat and do my r squared now. It should be 9.00 meters squared. Remember, when you square something like this, you must square the unit as well. It's not just 3 meters times 3 meters equals 9 meters. Not a chance. It's 3 meters times 3 meters is 9 meters squared. And then, of course, the charge, which is my Q, is 1.25 times 10 to the minus 5 coulombs. So now I'm going to plug in the formula, plug in my values. So E equals KQ over R squared. So we'll plug everything in. So I'm going to write this out in kind of one line. And I'm going to try to explain what's going on here. So 8.99 times 10 to the 9 Newton meters squared. And now I'm going to make a bottom line with coulombs squared. So this is my K. Now I need my Q. And my Q was 1.25 times 10 to the minus 5 coulombs. So this is my Q. And now on the bottom here, I'm dividing by r squared. So that means I can sneak r squared right here. So bear with me. I'm going to put my 9 meters squared right on the bottom here. So we are allowed to do this because if we're dividing by a value that only has one unit attached to it, we can just straight up put it on the bottom. Now we need to clean up all of our units. Now I see a meter squared on the top here, on the numerator, and I see a meter squared on the denominator. So those are toast. I have a coulomb up here, but I have coulomb squared down here. Just to help you, oops, did not mean to do that. Just to help you, I'm going to write coulombs squared in a different way. This is some Math 10C. Should not blow your minds. What's a coulomb squared? It's a coulomb times a coulomb. Like A times A is A squared. Same idea. Which means that I'm allowed to cancel out 1 on top and 1 on the bottom. Which means the only unit that I should have on top is newtons, and I do. And the only unit I should have on the bottom is coulombs, and I do. That means that my unit right now is newtons per coulomb, which is the units we were looking for. That's field strength. So we did it. Now we just have to do the math. And the math is just a piece of cake now. So I'm going to go 8.99 times 10 to the 9 multiplied by 1.25 times 10 to the minus 5, divide it by 9, and I get a hilariously big number. So the number is 1, 2, 4, 8, 6 point repeating ones newtons per coulomb. We only have 3 sig digs to burn, so I need to make sure that I do my sig digs correctly. So 1, 2, 4, that's 3 sig digs. I look to the right and I see an 8, which means I'm going to go up. I'm going to round up. So this is 1.25 times 10 to the something. What is the something? Well, we put our decimal there, and we have to walk it 1, 2, 3, 4. So my newtons per coulomb, my field strength, is 1.25 times 10 to the 4 newtons per coulomb. You may have been wondering why there's absolute value lines or absolute value bars around these. The reason why is because we don't differentiate between a push and a pull in Science 30. All we care about is how big is the force or how strong is the field. Do we know if this is an attraction or a repulsion? No, because we haven't put a test charge in there. So this is what we're going to do on the next question. So here's how we would ask this question to you in Science 30. And I'm going to give this a positive value. So what is the force experienced by a 2.5 times 10 to the minus 6 coulomb, oops, I should say charge there, test charge, if it is 700 meters away from a 3.15 times 10 to the minus 5 coulomb field? So the first thing we're going to do is figure out how strong the field is, Then we'll plop this guy into the field. So first of all, we care about the strength of the field, which is the formula K times Q divided by R squared. You might be wondering, oh God, what do we do? There's two numbers here. They're both coulombs. Which one do we use for this? Well, the one that's attached to the field is going to go here. That should make sense. It says field, so this is generating the field we care about. I know that they both have a field, but this is the field that we care about. So as usual, K is 8.99 times 10 to the 9, and that's Newton meters squared per coulomb squared. An absolutely goofy kind of number, but again, it's okay. It's not going to kill us. Then we have Q, that's the charge of the field. So the charge of the field is 3.15, negative 3.15 times 10 to the minus 5 coulombs. And my distance, my R, is 700.00 meters, which I have to square because R squared is what we care about in the formula. So I'm going to just do 700 squared, which is 490,000 meters squared. So 490,000 meters squared. So we've got everything written down. Now I'm just going to plug it in. So here's my field strength, E, absolute value with a bar. I start with K, 8.99 times 10 to the 9 Newton meters squared per coulomb squared. There's my K. Then I do my Q. My Q is negative 3.15 times 10 to the minus 5 coulombs. And my R squared is 490,000 meters squared. So we do the math. We're able to cancel out meters squared. We take one of the coulombs out. Remember what we did before? I wrote down C times C, and I crossed out one on top and one on the bottom. Here, I can just cross out the square. It's the same thing as crossing out one of the C's. So I'm going to do the math, and actually I'm not even going to bother with the negative because we can understand later on whether the field is an attraction or a repulsion. If we've got a positive test charge in a negative field, positive and negative are going to attract. So that gives us the understanding that it's a attraction in our case. So let's do the math. So 8.99 times 10 to the 9 multiplied by 3.15 times 10 to the minus 5 divided by 490,000 is 0.5. So I'm not doing sig digs because I'm not done the question. 3. I'm just gonna, in the interest of not writing down a bunch of numbers, I'm gonna hit the brakes there. And this is in newtons per coulomb. So, for example, if my test charge was 1 coulomb, it would experience this amount of force. If it was 2 coulombs, it would experience 2 times this force. If it was 1,000 coulombs, it would experience 1,000 times this force. But it's not any big number like that. It's a tiny number. So here's step 2. I'm going to take the field strength newtons per coulomb, and I'm going to multiply by the other coulombs, the other charge, 10 to the minus 6 coulombs. What is that going to give me? What's the surviving unit? If coulombs cancels out coulombs, the only unit that we have left is newtons. Units matter, guys. All too often, not just in the classroom, but I'm going to expect that here too, that a lot of you guys just ignore units. It's going to just burn you. If you're going into university in like a general degree where you have to do a little bit of math or a little bit of science type stuff, if you don't put units, it's gonna destroy you. So when we do questions in Science 30, you better believe that we write down our units in every part of everything, we cancel them out appropriately, and all of that. And the reason why, like I said before, is it helps you find out what the answer is. If I did all this work, and I have newtons as my answer, hey, the question's asking me what is the force. Newtons is how we measure force, and that means that we're smart. We did it, we did the thing right. So let's do the math. So 0.57793 multiplied by 2.50 e negative 6. We get 1.44. Let's see, we only have 3 sig digs to burn, so we'll have a 1.44 times 10 to the minus 6 newtons. So it's not a big, strong pull. It's not a lot of force. Partly that's because we're far away from the force, or from the field. If we were closer, this number would be much higher. So this is how we figure out electrical field strength. So we've seen electrical field strength and we've seen gravitational field strength. We've seen that they rhyme. And I'm going to be filming the gravitational one and putting it up right after. I did them in reverse order, but you'll see both, and you'll see that then I'll give you a little bit of a compare and contrast. So see